Hello to this video. In this video, we are going to talk about where the magnetic field is coming from that we need for generators. So if we want to run a generator that is based on turning motion energy into electricity, this is all based on Faraday's law of induction. And we have seen that Faraday's law of induction is based on having a magnetic field, and this magnetic field is changing or something is rotating in the magnetic field, but we do need a magnetic field in order to induce a voltage. If we don't have any magnetic field, we don't have any induced voltage. So because of this, it's really critical that we have the magnetic field, and we also have to have an idea of how large the magnetic field is. So for the different options that we have to generate the magnetic field, the first one obviously that we can think about is to use permanent magnets. And permanent magnets are one option that is used in wind turbines also. So you can use permanent magnets in order to generate this magnetic field, or we also have the magnetic field here to generate this magnetic field. So permanent magnets is option one to generate the magnetic field. And for the permanent magnets, we will hear more later in a different video of what kind of materials are used in order to have obtain such a permanent magnet and how strong the magnetic field is. I will talk today in this video about electromagnets. That means this field B here that is needed for induction is generated by a coil itself following the experiments of Ørsted. And let's look at this generation of magnetic fields with using the principle of electromagnets. So we already saw that Ørsted was doing experiments and observed that a compass needle around a conductor is changing its orientation depending on if it's on this side or on the other side of the conductor here. So in these experiments, Ørsted saw definitely the current through a wire is generating a magnetic field, and the magnetic field is described by the right-hand rule. That is, the compass needle will be oriented differently on one side of the conductor than on the other, and this is described by these field lines that show the orientation that a compass needle would have by the arrow given that is giving the orientation of the compass needle. So Ørsted saw that we have around a conductor we have a magnetic field. So from this we already know we don't really need a permanent magnet. We can just go ahead and have wires basically, and the wires generate the magnetic field. So if we look at this in more detail, we of course need to know, so how much magnetic field do we get if we have this wire here? How large is the magnetic field at different positions? In order to calculate then later on, how can we build the generator? And this consideration, all of the experiments that first Ørsted and later on Ampère also did, are summarized in Ampere's Circuital law. And this is the law here, and what it says is that if you integrate along a closed contour, so this here means that we have a closed contour around the surface A, and you integrate the magnetic field H along this contour, the result is equal to the electric flux through the contour. So if we are considering this inner loop here, so this loop here of the magnetic field, we see that we have the current I going through. So here the magnetic flux would just be the same as the current I. And then if we are going to the next outer one, so to this loop here, and integrate once along the complete loop, also the electric flux is the same I, and the same is also true for the third loop. So that means that we learn from this here that as we are further away from the conductor, the integral, so the path length, the contour integral is a longer path, and that means because the path is getting longer, the H field is getting lower. So the H field is dropping as we increase the distance from this conductor. So let's look at this at a bit more detail. First of all, I defined here for you that the theta is the electric flux through the bounded surface that we are considering. And so if we are considering a certain contour line like this one here or that one here or the one down here, that means we take the surface, we consider the surface that is bound by the contour line, and all the currents going through the surface will contribute to this electric flux here. And for constant currents, the overall electric flux is just the sum of the different currents. Also, what we see from this here, if the flux is constant because we have constant currents, it means we also have a constant magnetic field because we don't have any time dependency. So if you consider a certain loop, we have a constant current, we also have a constant field. So that is why we talk about magnetostatics. We have a stationary current, a constant current, and this causes a constant magnetic field. Magnetostatics, no change in the magnetic field over time. Let's look at some examples of how this electric flux here is calculated. So this is the first example I brought you, and how this representation is done now is that this sign here, this cross, means that the current is flowing into the page. And this you can kind of imagine like this dart file, this dart here. So if you have such a dart, you can see that if it is flowing into the page, so it's flowing into the page, then it means that you can see here this cross of the backside of the dart, and that is exactly what is shown here. So this is like the cross of the backside of the dart, means it's going into the page. If a current is coming out of the page, then you see the tip, and this would just be indicated with a dot in here. So this notation that you have a cross or a dot in a circle means that the current is going orthogonally to the plane of the surface, into coming out of the surface or going into the surface, as in this case here. So here in this case, the current is going into the surface, and that would mean it generates a magnetic field by the right-hand rule that is oriented in this direction. And now you can see that the contour line that I chose here, this contour line has an orientation in the other direction. So it's opposite to the direction that we get from the right-hand rule. And that, if that is the case, it means that this current here needs to be counted negative. So for solving the integral, this electric flux now here is minus 5 ampere. So the electric flux is minus 5 ampere if we have this current going into the page. Let's look at a second example. So this example here, again, I defined a contour line. And maybe I should say at this point that this contour integral here is true for any kind of contour line. So it doesn't say it has to be a circle, or it can be a rectangle, it can be an arbitrary shape, an ellipse, or here I chose a rather arbitrary shape, as you can see. So it can be some arbitrary shape. You can take any shape for choosing the contour. And how the flux is then calculated is that you have to consider all the currents that are within the area that is bounded by the contour. So if this is the contour, we can see that this current here is inside the area that is bounded by the contour. This current here, it's not inside the area that is bounded by the contour. So here, in order to calculate what the electric flux is, you only count in this current, because you only need to consider the currents that are on the surface, that cross the surface, bounded by the contour. So that, first of all, means it doesn't matter for Ampere's circuital law that there's another current source here. We only need to consider this current source. Then this current source is coming out of the plane, so it's coming in this direction, and again we check the direction and we see that this here, in this case, we have 2 ampere, that is the the direction is agreeing between the current direction that's coming out of the plane and the right-hand rule by Ørsted. So the current is counted positive, and we have a total electric flux of 2 ampere. The other current 2 doesn't matter that it's there because it's not going into the integral. So you might now say, well, that is a bit strange because, I mean, it's there, the current. So how, and it should do a magnetic field also. That is completely true. Of course, this current also generates a magnetic field. And what the Ampere's circuital law here is talking about is what is the total magnetic field if you, or what is the integrated magnetic field if you integrate along the contour. And how you can resolve this paradox, as it seems, is by considering that the contour is going up here on one side and it's going down on the other side. So basically, if you consider this current source, it will do a current around it, but it will count positive into the line integral on one side of this contour, and it will count negative on the other side of the contour. So because of that, the magnetic field of this current source here, it will vanish if you have it once positive counted in and once negative counted in, because in Ampere's circuital law you have to consider what is the direction of integration, and the direction of integration is the direction given by the arrow here. So because of that, this doesn't count in, and it doesn't mean that there's no magnetic field due to this conductor. It just means that if you take the integral over the contour that is shown, this doesn't need to be considered. If you take a different contour, so if you would go kind of go around both of the conductors, do a loop like this, then you would need to consider both of the current sources for evaluating Ampere's circuital law. Third example, to have a few more current sources here. So this is the third example we are considering here. So here we again have conductors that are coming out of the plane. And you can see that if they're coming out of the plane, first of all, the rotation direction of the contour that I have shown here, so of this contour here. So the rotation direction of this contour here is the same as we have Ørsted's right-hand rule orientation. So the currents that are positive, that have a dart tip showing, will count positive in. And here we have now 3 currents that are within the bounded surface, so they need to be considered. We have a 4th current that is outside, that does not need to be considered. And I have one more extra case here that is often happening, and that is that now we have a constant current I3 here that is pointing out of the plane here, but it's negative. What does that mean? Well, if you are defining currents, you typically define, first of all, a direction for the current I in order to give it some name and some orientation. But in reality, the physical current might flow back and forth along the conductor, actually. It might change over time if it's going one direction or the other. And so to take care of this, the current might go over time in one direction and the other. You don't change the notation every time. What you do is you change the sign. So that means that if you have defined the orientation of I3 coming out of the page as here, as the positive I3, a negative I3 means it's actually flowing the other direction. That is, it's going into the plane, so it's going in the other direction physically. For calculating the electric flux, this just means you have to add this in with a negative sign. So that means the total flux is 1 ampere plus 2 ampere minus 2 ampere. And so the total flux here is 1 ampere for the evaluation of Ampere's circuital law. So this is how the flux here is determined if you have any numbers of conductors in your plane. And then you can, for a defined boundary, calculate what the flux is and then use this in order to learn more about the magnetic field. typically what is done is that you try to choose this boundary such that you have a highly symmetric situation. That is, if we go back to this graphic here, so typically you choose such symmetric lines around the conductor, because then you can in the calculation say, well, if it's completely symmetric, then the magnetic field must be the same on this side as it is on the other side of the conductor over here. So the magnetic field on the line here must be the same magnitude as the magnetic field here, because it has the same distance to the conductor. And you can use this symmetry reasoning in order to put additional constraints on the H here. So you can say the magnitude of the H is the same, it's only changing its direction when going around the conductor. And that we will see in a math example later on how to calculate it. But that is why typically boundaries are chosen that are completely symmetric, because then you can actually use this integral in order to this integral law in order to derive how large the magnetic field is. But it's only an integral quantity, and what we saw previously, if you have very complex contours or situations, it's very difficult to evaluate this here, but it's always true. So it holds true, the law. It's just a question of, is it useful for you to evaluate how large the magnetic field is, which you want to do in order to build electromagnets. Going one step further, in general, this electric flux does not need to be confined to specific conductors going through the plane as we were considering so far. It can actually be also distributed over the surface. So if you have a surface here, it could be that this surface has everywhere a certain current density passing through it. And the current density would be described by this J here. So the current density J through the surface could be depending on the position, for example, and then it means the flux is calculated by integrating the current density J over the surface area A here. Also, in general, we might have additional effects, and that is a changing changing electric field here, as we see in this term, that is also generating extra flux, and we will look at this in another video of where this term here comes from at the end. But just to tell you in general, this is what the electric flux is for the most general situation. And actually, this equation here for the general electric flux equation plugged into here can then be combined, and I will just show you the combined form. So this is Ampere's Circuital law. If you combine all the different flux effects you might have, then you get this general situation. And if we only have conductors, then we can just use the theta, the combined flux. It's often easier than taking the integrals. But if we have a current density that depends on the position of the surface bound by this contour integral, then we need to consider this more general shape. The same if we have changes in the electric field, we also need to consider this general shape. So this is Ampere's Circuital law, which is very helpful for calculating highly symmetric configurations. So if you have highly symmetric configurations, you can use this and calculate the magnetic field. It has the disadvantage that it's an indirect, it's only an integral relation between the magnetic field and the flux. There is another law, which is the law of Biot-Savart, which allows you to calculate the magnetic field H directly. And the law of Biot-Savart, which was also found experimentally and then formulated mathematically, is that the H field is given by I over 4 pi, and you have to integrate along the conductor with length L through which the current I is flowing. So you have to integrate along the conductor, and you have to integrate dl in a cross product with this vector r here, which is the distance vector between the piece of the conductor and the point of interest where you want to calculate the magnetic field. And the whole thing then goes over the distance between the point of interest and the conductor piece to the third power. And also here we are going to look at examples of how the law of Biot-Savart is used to calculate the magnetic field. So these are the two most important, I would say, relations in order to calculate how large a magnetic field is that you generate electrically. And coming back to this, we want to do induction. We need for induction to generate electricity from motion. We need to have a magnetic field. We can get the magnetic field as first option by a permanent magnet, or as second option, we can get it using this Ørsted effect that the conductor also has a magnetic field around it, and we can use this magnetic field. Of course, you have to consider, if you do that, you need an initial electric field to even generate the magnetic field in order to get the induction. So in this kind of scenario, you cannot start out with having no electricity at all. Because if you don't have any electricity, you cannot generate any magnetic field, and then you cannot do induction. If you use a permanent magnet, you have the magnetic field without any electricity and can basically generate electricity with no electricity there. But for this scenario here, you do have some basic electricity need already to generate the magnetic field. And of course, this is working anyways, and that's why it's used so much, because the electricity, so the electric energy you generate, is a lot larger than the electric energy you have to put in order to get the magnetic field for the induction. Because we don't have just this, that we are converting electric field to magnetic field and then magnetic field to electric. No, what we are doing is we are converting electric field to magnetic field. Then we have the motion energy of the turning coils, for example, and this is where the difference of energy comes from that we then see in the electricity. Thanks for watching.